In this video, we'll be talking about heat, the types of heat transfer, and imagine a scenario where you're trapped in the Rocky Mountains in the middle of the winter, but you're given a hot cup of hot chocolate along with a little can of creamer that's at the same temperature as the surroundings. How would you keep the hot chocolate as hot as possible for as long as possible? But to get to that question, we'll start out with a definition of heat as energy transfer that's due to a temperature difference. And we'll look at one of my favorite examples of a can of beans. So this is a can of beans, and we'll take a zoomed in image of one of these beans. So zoomed in, we have that same bean on a super large scale, and we'll say that bean along with the can was just in a regular room, so it's just at room temperature. And let's say we decide to bring it outside where our hot sun increases the air temperature to be 300 Kelvin. Now, heat describes the energy that enters the can of beans and results in a temperature increase for the bean. Because there's a temperature difference between the surroundings and the bean itself, right here, energy will be transferred from the area of higher temperature to the area of lower temperature. And this is described by equation. So we always talk about heat transfer. So this dot represents the derivative with respect to time. So over time, heat transferred is equal to some constant. So this depends on the specific properties of whatever you're looking at. Because we're just looking at a bean, we won't focus too much on it, but it's just a constant. And that constant is multiplied by the area, so the surface area. So it would probably be, for this specific bean, just the surrounding of the bean right there. And this is multiplied by the temperature of the surroundings minus the temperature of our system that we're looking at. So if we're just looking at this bean, then this would be the 295.15, and this would be that 300 Kelvin. And so this causes heat to be transferred into the system. And there's also different types of heat transfer. There's different types of heat transfer. If we imagine a campfire, so we have some wood and we have our little fire. There are three main types of heat transfer that we'll look at. The first one is conduction. So if we have some sort of metal bar, imagine we're trying to toast a marshmallow. So this is a little marshmallow at the end of a stick, and it's being toasted a little bit. If we have our hand on this metal bar, so just draw a little box for hand, along with a little thumb. The heat transfer through this metal bar is called conduction. with the air above the fire heats up this air, and it keeps on causing collisions, and this mode of heat transfer is called convection. And the last one that we're interested in is radiation. So this one's a little bit harder to grasp, but this fire is emitting electromagnetic waves in the form of visible light. So it's emitting these high frequencies, or these waves with a frequency that our eye can detect. So there's an eye, we're kind of seeing this fire, and so this is emitting radiation. A non-harmful form of radiation, but radiation nonetheless. So this brings us to the question that was posed earlier. So let's imagine you're on a mountain. So this is a little mountain range, and it's the middle of the night, so the air is pretty cool. Luckily for you, you run into a store, and I won't say its name, but this is a recent logo that they just added. And let's say you're in this mountain and you're given a hot cup of cocoa. So this is a hot cup, and then you're also given a little can of creamer. This creamer is at the same temperature as the environment, so this is pretty cool. In order to keep the temperature of the hot cocoa as high as possible for as long as possible, what would you do? Would you add the creamer? Would you do it right away? Would you do it after the cocoa has cooled? When the cocoa is completely cold, so same temperature as the surroundings, does it not matter? And this is just a stupid question. Or do you not care because you don't like hot cocoa? So after thinking about it for a second or two, the idea is to actually add the creamer right away. And this is because of the equation that we introduced earlier. So remember, the heat transfer with respect to time is proportional to the temperature difference between the surroundings and our system right here. So at the very beginning, as soon as you get that hot cocoa, the temperature difference is very high. So we'll write time right here, and we'll have T difference, or the temperature difference at the very beginning. This is very high because you just got that hot cocoa, and it's very hot in reference to the surroundings. Now after a little bit, so some time later, this temperature difference might still be there, but it's definitely smaller. And then after a long time, there's not going to be any temperature difference because the hot cocoa becomes the same temperature as the surroundings. Because the temperature difference is greatest at the beginning, this is going to cause the most amount of heat loss. So if we add another little column here, heat loss, it's going to be proportional to the size of the temperature difference. So it's also going to be greatest in the beginning, still there but not as large sometime later, and then not there at all after a long time. And so the idea is that you add the creamer right away, you cool down the hot chocolate to be a moderate temperature so that the heat loss is not as great. Thank you for joining me on this video. I'll see you in the next one.